Hello, my name is Rob Reynolds. Welcome to Business Calculus, Chapter 3, Section 6. Today we're going to explore asymptotes and their limits, probably to infinity. So first of all, we need to define that vertical asymptotes come by setting the denominator equal to 0. Horizontal asymptotes, I'm going to give you three scenarios whether the degree of the exponents are less than, the numerator is less than the denominator. And we're looking at the exponents, so the numerator is less than the denominator if the numerator is equal to the denominator, or if the numerator is greater, the exponents. The exponents numerator are greater than the denominator. So we're going to have three different kind of scenarios of what happens with these horizontal asymptotes, and then we're going to use asymptotes in a real life situation. So again, asymptotes are these vertical. There's a vertical asymptote here at looks like x equals 2, and then we got a horizontal asymptote probably at y equals 4. Just looking at the graph. So you can see vertical asymptotes come by setting the denominator equal to 0. So x minus 1 equals 0 when x equals 1. So for this one you can see, there's a vertical asymptote at x equals 1. It looks like there's a horizontal, they didn't draw it in. Looks like it's at y equals 1. And talking about the degree of the numerator again, here the degree of the numerator is 1, the degree of the denominator is 1, and so if they're equal, you do the coefficients out front. So the coefficient here is a 1, the coefficient here is, and 1 divided by 1 is y equals 1. So it's easy if the degrees are the same, you just do the coefficients out front. So horizontal asymptotes, again, go vertically, horizontally. Like this, there's a vertical, and then we have something called an oblique, and that's when the numerator degree of the exponent numerator is greater than the denominator, and oblique just means slanted. And sometimes we can even find the equation of what that is. Maybe it starts at 3 and has a positive slope of 5 or 1/5 or something. So sometimes vertical asymptotes, as they approach maybe 2, they'll go to positive infinity from the left, and they'll go to maybe negative infinity from the right. So here's the answer for, and this is how to denote, approaching 2 from the left. This little sign right here means from the left. And this little plus sign right here means, I think I wrote left, but this should have been right, right? From the right, it goes to positive. So if it's approaching from the right, this is from the right, and this is the function approaching from the left. I think I wrote that wrong. This is another explanation where if you have the function y is equal to 3 over x minus 2, you set the denominator equal to 0, and there's your vertical asymptotes. And when you have vertical asymptotes, you can start talking about the limits as it approaches from the left and to the right, and oftentimes they'll alternate. Sometimes they're the same. You might have a graph with 2 vertical asymptotes, and maybe it'll look like this. And so you can see, usually if this is positive infinity on this side, this will be negative infinity. But there are cases where you have vertical asymptotes, and they do maybe something like this, where kind of looks like a volcano. And that's called a double. So you might have, I don't know, 5 over x minus 3 quantity squared. So there's 2 vertical asymptotes at x equals 3 and x equals 3, and that's what causes it not to alternate but go the same direction. So if it's even, it's going to go the same direction. If it's an odd 1/3 factor, then it's going to alternate. So again, here it is. The limit as x approaches 1 from the left. And so you could think about a number line. Here is 0, here is 1, and something really close. It's the limit. So I picked like 0.999. This is just kind of what we're thinking. You can see that this is going to be a small positive number, really small. So you need to know that 1 divided by a really small number gets really large, like we'll call something really large infinity. But since it's negatives out front, we'll say negative infinity. So you could graph this and just look at the graph, but you should be able to evaluate it by thinking, let's think of a number to the right of 1.1. So, by the way, this answer better be negative infinity. Good, it is. So this is negative infinity, so this is this problem. So over here, we're approaching from the right, and so approaching from the right, we'll think, something like 1.0001, something really close, but you can see this is going to be positive divided by positive, so it's really small though, so it's going to be positive divided by a really small number is positive infinity. So I'm hoping this says positive infinity, yay. Good. So this positive infinity is this positive infinity. And if all else fails, you could just graph this on your graphing calculator and actually just look at the function, and you can see from the right it's going to positive infinity, and then from the left, I think I've used all my colors so far, so I'll go to orange. From the left, here's the approach from the left. Good golly. There it is, approach from the left. You can see it's going to negative infinity right there. Another hint is just to try to let you know if a function is positive, this whole fraction is positive, you know you're going to be in the first quadrant. If it's negative, you're not in that first quadrant. You might be, I don't know, it might be down here altogether, but if it's negative, you're just not in the first quadrant. So you can see this one's positive, this is in the first quadrant, but it might not be first and third, it could go like this. And if it's negative, well, there you go. It's just not. All I know is it's not in quadrant number 1. Could be somewhere else. So that'll kind of hint to you what these graphs look like. For example, this one's negative, so I know it's not in the first quadrant. And not in the first quadrant. So again, you do some thinking here, or you could just take this and go to your y sub 1 and graph it. And you can see, from the right, it's going to negative infinity, and then from the left, I'm going to positive infinity. So maybe pulling out your graphing calculator and looking at would be easy. Here's that double root that I was talking about, x minus 1, x minus 1. So you can see x equals 1 twice. So when that happens, you have a double vertical asymptote, and that always causes the volcano. But you don't know if it's a volcano coming in the positive direction or the negative direction. And in this one, you can see because it's not in the first, it's going down. And that way, both answers are negative infinity. So from the right, it's negative infinity, and from the left, it's negative infinity. So hopefully you're following along with your 3-6 worksheet, which you can download from Blackboard, and you can determine what the answers are for Part D, which I have outlined here as positive infinity and positive infinity. Again, when you got the double asymptote, they should be in the same direction, either both positives or both negatives. So when you're finding vertical asymptotes, the goal is to factor the denominator and set it equal to 0. So we've got a vertical asymptote at 0 and at 2. Of course, you're welcome to graph it and look at how the function looks. So here's the 0 and here's the 2. Oftentimes we can't tell if it's exactly 0 and 2, and that's why you want to make sure you can do it algebraically. For this one, this is the difference of 2 squares, so we have a vertical asymptote if I factor this at x equals negative 2 and at x equals positive 2. So vertical asymptotes. We could talk about horizontal asymptotes, but all they asked for right now is vertical asymptotes. So the definition for vertical asymptotes is set the denominator equal to 0. So there's a trick here. You can see, you would think you would have 2 vertical asymptotes, but because the numerator over here also factors of 8 that differ by 2 are 4 and 2. Signs are different. The larger term is positive, x plus, x minus. Actually, this x minus 2 is not a vertical asymptote, so this is kind of a trick problem, and this is called a removable. And it doesn't cause a vertical asymptote, it causes a hole in the function at 2 comma f at 2, well, whatever the left. So that's why they say the new function is really just this, y is equal to this, because this is called the removable, which creates a hole at x equals 2. So again, that won't probably show up on your graphing calculator, but it will look something like this. I encourage you to graph it, but you won't see this hole, so it's really deceiving. So this hole is called the removable, and this right here is the only asymptote for this particular function. So again, your graphing calculator won't have that open dot there, so it's really deceiving. But you can see certainly there is no vertical asymptote because it's not going to positive infinity or negative infinity. at the asymptote. For example 4, we're saying find the limits. So of course we've got an asymptote there, so you can't just do direct substitution and plug in a 1. So again, we're going to think of something to the left. So we're going to test like 0.999. And so if I plug 0.999 in, well, let's factor this. This is x and x minus 3. So I'm going to use x minus 3 over x minus 1. So if I plug the 0.999 in here, this is positive times, this is going to be negative, all divided by, now if I plug in a 0.999 down here, it's going to be negative. So you can see the function is going to be positive, but what I'm really interested in is down here, it's some number, which I don't even care what it is, but down here, it's, if I plug in the 0.999 down here, minus 1, it's really tiny small. And any number divided by a really small number, you can try it on your calculator, like any number, 5 divided by something really small gets really large. So that would go to positive infinity because negative divided negative is positive. Let's repeat this process. If you were to test, let's let x equal 1.0001, and I'm going to plug it into here again. And so this term is positive because 1.0001 is positive. And this is negative again. And then down here, this turns out to be positive this time. So again, this is negative divided by something really small down here. And a negative number besides just infinitely small gets infinitely large, and we'll say negative infinity for the positive. Again, you can welcome to pick up your graphing calculator, just graph this thing and check it out. You can see it's going infinitely large, positive infinity from the left goes positive infinity, and then from the right it's going to negative infinity. Horizontal asymptotes, I told you to look at the degree of the numerator and the degree of the denominator. Here's the book's definition. I think I can explain it a little bit better. The only thing you have to worry about is sometimes they have like a +4, which is literally going to just shove this asymptote up 4 from this degree of the numerator and the degree of the denominator. So if the function just said y is equal to 1, x minus 2, without the +4 out there, you can see the degree of the numerator is a 0. There's no x's up top. The degree of the denominator is a 1. And I haven't given the rule yet, but if the numerator degree is less than the denominator, it's y equals 0. But because they say +4, it starts at 0, and then I shove that up 4 units. So be careful for those types of scenarios. There are other types of horizontal asymptotes. Sometimes we can have more than one horizontal asymptote, and sometimes you can actually cross a horizontal asymptote. Not usually, but if some functions there have some exceptions, you can never cross a vertical, but you can cross a horizontal, and you can have more than one. Here's what we're talking about when it goes to 0. We've already talked about on previous slides, 1 divided by a really large number or a really big number goes to 0, but 1 over a really small number goes big. It's the opposite of what you would maybe think. But 1 divided by, so 1 over a lot, you can see that's approaching 0. It doesn't ever get to 0, but boy, it's really small. So if I'm talking about the limit and it's going to infinity, then we would say, yeah, it approaches 0. Remember, it's not, limits aren't about what it's at, it's about what it's approaching. So you can see you can't just plug this in directly. So we could actually break this up minus the limit as x approaches infinity of 2 over x squared. So the limit as x approaches 5, well, that's easy because that's just 5. If you look at the graph of y equals 5, it's just a horizontal line. And as you go off to the right to infinity, it's still just 5. Minus, and so this is 2 over a really big number. And of course, that's like saying 5 minus 0, which is just 5. So this guy goes to 0. They've actually popped out the 2. You don't have to if you don't want to. But 1 divided by a really big number is really small. This makes sense when I look at the horizontal asymptote because the degree of the numerator is less than the degree of the denominator. So this tells me y equals 0. But then this, well, I could rewrite it. So negative 2x to the 0 over x squared. So this says 0, but then I say plus 5, so this goes up 5 units from y equals 0. So that makes sense, going to positive infinity and negative infinity. The horizontal asymptote approaches 0. So again, either you could do it algebraically, or you could think about where those limits are. So let's try it. Find the horizontal asymptote, so I'm going to check out the degree. If the degree of the numerator is less than the degree of the denominator, then I literally just look at the coefficients out front and say, okay, that's the answer is going to be negative 2/3, and I'm literally done. How could I do this through limits? It's a little bit more complicated, but not much. The limit as x approaches infinity of negative 2x plus 3 over 3x squared plus 1. You may see that the author wants you to multiply the numerator and the denominator by a unique value of 1. I'm going to choose the highest exponent. And then when I distribute this to every term, I'll get the limit as x approaches infinity of negative 2 over x plus 3 over x squared divided by 3 plus 1 over x squared. And you can see this goes to, if I evaluate the limit here, this is negative 2 over a really large, so that's 0, or negative 0, plus 0 divided by 3 plus 0, and of course that goes to 0. Whoops. So 0 is the correct answer because the degree of the numerator does, oh my gosh. So if, I'm glad I worked it out by hand. So sorry. If the degree of the numerator was equal to the degree of the denominator, then I check the coefficient out front. Can I start this all over again? Look, the degree of the numerator is less than the degree of the denominator, so you do not do the coefficients out front. It's not this. It actually is 0. Oh my goodness. Where did I write that? If the degree of the numerator, where are those rules? I just need to get them for you. I think I have them on a slide here. I bouched that. Here, oh, here, this one works. If the degree of the numerator is equal to the degree of the denominator, so this one is going to be the negative 2/3. And again, you could do that through some algebra, which, again, we'd multiply top and bottom by probably the same thing. Look at this. If the degree of the numerator is greater than the degree of the denominator, then we know that it's oblique, or it's slanted. And for the purpose of this video, I'm just going to say there's none, because they literally are just asking, what's the horizontal? And it's not horizontal. So we could write the equation of the oblique asymptote. Sometimes we do that by long division, but I don't want to freak you out on this particular lesson. And then we could find that equation up here, but they didn't ask for that in this slide, so we won't look for it. So for 6a, again, we said the degree of the numerator is less than the degree of the denominator. That's why the horizontal asymptote's at y equals 0. It's interesting, this does cross here. You don't know why yet, but it hovers, it kind of comes down below and then approaches. When it gets to infinity, it's going back to 0, but it actually crosses the horizontal asymptote. This one, since the degree of the numerator is equal to the degree of the denominator, again, all we had to do was check the coefficients out front. And so this right here is at y equals negative 2/3. There's a lot of calculus here. And there's the oblique asymptote, which you have to do long division. Take the bottom and divide it into the numerator to find that actual y equals mx plus b line. And it doesn't always have to be a line, but for this applications, or for our purposes, it probably will. Applications. So we're going to look at the average cost function and how asymptotes behave on an average cost function. So we've talked about average cost before. If C is equal to 1/2, because it's 50 cents per unit, 1/2 x plus the start value, which is 5,000, the average cost is divided by x, because remember C bar was C divided by x. So nice definition you should have memorized. So this is just going to be 1/2 plus 5,000 divided by x. You could think about that as 0.5 plus 5,000 x to the negative first if you have to take the derivative of that. So part A just tells you to take 1,000 units and plug it in right here. So I wouldn't go to this guy yet. I would just go 1/2 plus 5,000 divided by 1,000. That's my average cost. and I think that turns out to be $5.50. The average cost per unit for 10,000. Oh, I do the same thing. 1/2 plus 5,000 divided by 10,000, and that'll turn out to be $1. And the average cost per unit for 10,000, oh, same thing, and that turns out to be 0.55. Then part D is the limit. So you can see what it's approaching. So they start at 1,000, move to 10,000, move to 10, and so it's moving from $5 to $1 to 50 cents. What do you suppose this is going to approach? Well, you would think maybe 0. But if we push this to infinity, we get the limit, we get the limit as x approaches infinity of 0.5, no. We want to use the average cost. Yeah, the average cost limit. So the limit as x approaches infinity of the average cost function, which is 0.5 plus 5,000 over x, then this is 0.5 plus 0, because we know 5,000 divided by a really big number goes to 0, and the limit is then 0.5. That would be the way I would explain it. Here's the author's explanation, which I haven't honestly read, but hopefully they'll end up with... Oh, so there they go. So there they start with the average function. Oh my gosh, there's answer A, there's answer B, there's answer C, and then does he have an answer for D? Yeah, there it is, 50 cents. So again, we could look at this and we say, oh, we actually have a horizontal asymptote, because if it goes to infinity, it's actually approaching y is equal to 1/2. And that concludes the lesson. A, B, C, I don't know why I'm doing these again. I think that's all the slides. All right, excellent. I hope you found this video helpful. If you have any questions, feel